coming up. More problems for a troubled
Earthquake.
crater. Yep,
We're having an earthquake.
The Earth beneath our feet is an ever-shifting puzzle, a testament to our planet's dynamic core. Crustal deformation data, a byproduct of this constant movement, offers an enlightening glimpse into regions where seismic tensions brew ominously. As we delve into this topic, one can't help but ponder, which locations within the United States are precariously perched on the precipice of significant seismic upheavals?
We really need to be prepared for that eventuality, because it's not a matter of if, it's just a matter of when.
Embark on this exploration with us as we unravel the mysteries of the Earth's tremors and pinpoint those areas standing on the front line of potential geological cataclysms. The dynamic nature of Earth's crust. The very foundation upon which we stand, live, and thrive, our planet's crust, is not as steadfast as it might seem to the casual observer. This seeming permanence belies a state of perpetual motion, dictated by the fierce and untamed energy emanating from the Earth's interior. The Earth's crust, split into several tectonic plates, floats on the semi-fluid asthenosphere, a layer of the mantle that allows for their movement. As these plates drift, they interact with one another, converging, diverging, or sliding past each other, leading to various geological phenomena, including earthquakes. Crustal deformation is a manifestation of these tectonic interactions. When two tectonic plates move towards each other, they might create mountains. Conversely, when they move apart, they can give birth to oceanic ridges. Sometimes the movement isn't so straightforward. Plates might get locked due to friction, preventing movement at their boundaries. However, the energy from the Earth's interior doesn't just disappear. It accumulates, deforming the crust, bending and twisting it under immense pressure. And when the pressure surpasses the frictional lock, it releases suddenly, resulting in an earthquake. Given the intrinsic relationship between tectonic plate movement and earthquakes, it becomes evident why the study of crustal deformation is invaluable. The patterns of deformation, when mapped over vast regions, give us insights into the stress and strain accumulating in specific areas. For instance, an area experiencing rapid deformation without any accompanying seismic activity might be a location where energy is amassing, signaling a possible future earthquake. Inversely, regions with slow deformation and frequent minor tremors might be releasing their tectonic stress gradually, thereby potentially reducing the risk of a large seismic event. It's not just about predicting when an earthquake might strike, but also understanding its probable magnitude. Regions with extensive, rapid deformation that have been quiet for centuries are particularly concerning, as they might be the sites of future large-magnitude earthquakes. Recognizing these areas allows communities to prepare, governments to regulate construction, and scientists to install monitoring equipment, all aimed at mitigating the impact of potential seismic events. But why is this so crucial? History and contemporary events alike bear testimony to the devastating power of earthquakes. From razing cities to ground, displacing communities, causing tsunamis, and changing landscapes forever, the repercussions of these natural events are colossal. Preparedness, based on accurate predictions, can dramatically reduce the loss of life and infrastructure. While predicting the exact time, location, and magnitude of an earthquake remains an elusive goal, the study of crustal deformation offers a step in the right direction. By interpreting this data in conjunction with other geological information, such as deep-sea trench formations, volcanic activity, and historical seismic records, scientists can develop probabilistic seismic hazard models. These models, although not pinpoint accurate, provide regions with a sense of the likelihood of an earthquake's occurrence over a specific time frame, giving them a fighting chance against nature's fury. Historical seismic activity, a precursor to present threats. When discussing the vast seismic history of the United States, one cannot help but be awed by the sheer magnitude and frequency of the events that have shaped its landscapes and affected its communities. The U.S., with its diverse geology, has been host to some of the world's most significant earthquakes, each leaving an indelible mark, not just on the ground, but in the annals of scientific research. The 1906 San Francisco earthquake stands out as a watershed moment in American seismic history. With an estimated magnitude of 7.9, this catastrophic event led to widespread destruction, consuming much of the city in flames and resulting in the loss of thousands of lives. This tragedy, however, spurred a revolution in seismic studies, leading to the formulation of the elastic rebound theory, the foundational principle that describes the mechanism of earthquakes to this day. Another prominent event, although less known outside geological circles, was the sequence of earthquakes that rocked the New Madrid seismic zone in 1811 to 1812. This series, with tremors felt as far away as New York City and Boston, showcased the seismic potential of the continental interior, a stark contrast to the more common edge-bound seismic activities. Alaska's 1964 Good Friday earthquake, the most powerful recorded in U.S. history with a magnitude of 9.2, reshaped vast portions of the coastline, elevated regions by several feet, and even caused parts of the coastal forest to sink and become submerged, creating eerie ghost forests. This event, apart from its immediate devastation, left an imprint on the science of seismology, allowing researchers to observe firsthand the massive releases of tectonic energy and the resultant tsunamis. Beyond these monumental events, the U.S. has witnessed numerous other earthquakes, each adding a piece to the puzzle of the country's seismic nature. California's San Andreas Fault, Oregon's Cascadia subduction zone, and even the less active but equally significant eastern seaboard have all contributed events that have, over time, given us a clearer picture of the nation's seismic profile. But how does the rich tapestry of America's seismic history aid in current predictions? The answer lies in the patterns. By studying the intervals between significant earthquakes, the locations of epicenters, the depths at which they occur, and the types of geological formations they affect, scientists can discern patterns. These patterns, while not deterministic, provide probabilistic models that indicate the likelihood of future events. For example, if a particular fault has historically produced a significant earthquake every 100 years and hasn't done so in the past 90, it might be deduced that the region is due for a seismic event soon. Furthermore, historical data, especially when paired with geological markers such as offset streams, raised beaches, and layers of sediment disrupted by past tremors, offers a timeline. This timeline, extending hundreds to thousands of years in the past, offers a broader perspective than our relatively short observational history. It's a window into the longer-term behaviors of tectonic plates and seismic zones, allowing for more refined and informed predictions. The Cascadia subduction zone, a ticking time bomb. Nestled along the Pacific Northwest, the Cascadia subduction zone is an enigmatic and ominous fault line, stretching from northern California to Vancouver Island. This geologic formation results from the Juan de Fuca plate's slow and inexorable movement beneath the massive North American plate. As these plates converge, immense stress and strain accumulate, leading to periodic releases in the form of powerful earthquakes. One such event, seared into the annals of geological history, is the 1700 Cascadia earthquake. With an absence of written records due to the pre-colonial nature of the region at the time, it might have remained unknown to modern civilization had it not been for the meticulous detective work of scientists. They pieced together oral histories from indigenous communities, sedimentary evidence from coastal marshes, and even historical records from Japan, which documented a mysterious, sourceless tsunami that reached its shores on January 26, 1700. This confluence of evidence painted a vivid picture. A massive magnitude 9.0 earthquake had struck the Cascadia subduction zone, sending waves across the Pacific. The implications of the 1700 event are profound. It underscores the immense seismic potential of the Cascadia subduction zone, a potential that has not diminished with time. If anything, with each passing year of tectonic pressure buildup without a significant release, the threat looms larger. Modern-day analysis of crustal deformation data in the Cascadia region paints a worrisome portrait. The data indicates significant strain accumulation, especially in the region's northern parts, This suggests that vast portions of the fault are locked, meaning they are not smoothly sliding past one another, but are rather stuck due to friction. As the forces from the moving plates continue to act on these locked sections, the energy accumulates, waiting for a moment of cataclysmic release. It's important to note that while the 1700 earthquake was the last great event, the Cascadia subduction zone has not been entirely silent. It has experienced smaller tremors and episodic tremor and slip (ETS) events, where deep portions of the fault release energy in a slow, non-destructive manner. However, these smaller releases, while relieving some pressure, do not negate the threat of a more significant event. If, or perhaps more accurately, when the Cascadia subduction zone produces its next great earthquake, the repercussions could be immense. Coastal communities would face the immediate threat of ground shaking, while a potential tsunami could impact regions as far away as Japan, just as it did in 1700. Infrastructure, from roads to bridges to buildings, especially those constructed before the modern understanding of seismic risks, could suffer significant damage. So, how do we navigate this looming threat? While the exact timing of the next major Cascadia event remains elusive, the study of crustal deformation, combined with other geological and historical data, allows for better preparedness. Communities can implement stricter building codes, ensuring that new structures can withstand intense shaking. Early warning systems, currently in development, might offer precious seconds to minutes of warning, allowing people to seek shelter. Education and community drills can ensure that, when the ground starts shaking, people know how to respond. The New Madrid seismic zone past meets present. The central United States, characterized by rolling plains and lush forests, is not the typical setting one envisions when discussing significant seismic events. However, beneath this serene landscape lies the New Madrid seismic zone, NMSZ, a hotbed of geological activity that starkly contrasts the tranquility above. Situated at the confluence of Arkansas, Missouri, Tennessee, and Kentucky, the NMSZ is not a product of tectonic plate boundaries like the more infamous faults of California. Instead, it lies deep within the North American plate, with its origins rooted in ancient geological processes. This rift complex, dating back hundreds of millions of years, is a testament to the immense forces at play beneath the surface. The seismic history of the NMSZ came to the forefront of public consciousness in the winter of 1811 to 1812. Over a span of mere months, the region was convulsed by a series of powerful earthquakes, the most significant of which are believed to have exceeded a magnitude of 7.0. These events were not localized tremors but widespread phenomena. They caused church bells to ring in Boston, over 1,000 miles away, and even led to temporary course reversals of the Mississippi River. The ground shook, fissures tore open, and landslides transformed the terrain. The aftershocks and repercussions of these events were felt for years. Entire forests were swallowed by the shifting earth, creating swamps and altering the landscape permanently. Settlements along the Mississippi River, still in their infancy, were decimated, and the region's sparse population was left traumatized by the scale and intensity of the events. Fast forward to the present day, and the significance of the NMSZ has not diminished. Contemporary crustal deformation data for the region shows that it remains seismically active. While the level of stress accumulation might be subtler compared to regions along tectonic plate boundaries, the potential for significant seismic activity persists. One factor that heightens concern is the geological structure of the central U.S. The Earth's crust in this region can transmit seismic energy over long distances with little attenuation, meaning even a moderately powerful earthquake could have wide-reaching effects. The study of the NMSZ today involves a combination of historical records, geological surveys, and modern instrumentation. By tracking the slow deformation of the Earth's crust in this region, scientists aim to understand the patterns of stress accumulation and release. While the intervals between significant seismic events in the NMSZ might span decades or even centuries, the historical record is clear. This region is capable of producing earthquakes that can rival those of the more infamous Pacific coastal zones. As research deepens our understanding of the NMSZ, the information plays a pivotal role in preparedness and risk mitigation. Infrastructure projects, especially those in proximity to the zone, factor in seismic resilience. Communities are educated about the region's seismic history, ensuring that they are not blindsided by potential future events. While the memories of the 1811 to 1812 earthquakes have faded with time, they serve as potent reminders of nature's unpredictability and power. Technological advancements and predictive measures. The endeavor to understand and predict the Earth's seismic behavior has been a centuries-long quest, akin to reading the moods of a sleeping giant. The complexities of geological processes, combined with the vastness of the Earth's crust, have historically made this task daunting. However, with the dawn of the technological age, our capabilities have expanded exponentially, painting a clearer picture of the forces at play beneath our feet. Modern techniques for collecting crustal deformation data have undergone revolutionary changes in recent decades. One such innovation is the Global Positioning System, GPS. While commonly associated with navigation, continuous GPS stations serve as vital tools for geologists. These stations, scattered across various landscapes, constantly measure the Earth's surface movement with incredible precision. Over time, these measurements create a detailed map of how different regions are shifting, tilting, or stretching. In seismic hotspots, such as the Cascadia subduction zone or the New Madrid seismic zone, these shifts can be indicative of accumulating stress. Another significant advancement is the advent of seismometers with greater sensitivity and range. These instruments can detect even the faintest tremors, ones that might go unnoticed by human senses. By deploying networks of these seismometers, researchers can triangulate the origins of seismic events, be they large earthquakes or minor tremors. The resulting data not only aids in understanding the immediate aftermath of a seismic event, but also offers insights into patterns that might foreshadow more significant events. Interferometric synthetic aperture radar, INSAR, further complements our observational arsenal. By capturing and comparing satellite images over time, this technique can visualize ground deformations down to the centimeter scale. Such granularity is invaluable, especially in regions where physical access is restricted or dangerous. With this influx of data, our analytical methodologies have also evolved. Advanced computational models, harnessing the power of supercomputers, can simulate various seismic scenarios based on current observations. These models take into account a myriad of factors, from the geological composition of fault lines to the temperature and pressure conditions deep within the Earth. By tweaking these variables, scientists can play out numerous what-if scenarios, refining predictions based on the outcomes. Yet with all these advancements, a critical question arises: how effective have we become at predicting earthquakes? The answer is nuanced. While we have made leaps in understanding the where and the how of potential seismic events, the precise when remains elusive. No tool or model currently exists that can pinpoint an earthquake's exact date and time. However, what these advancements do offer is a more informed sense of preparedness. Regions identified as high risk can prioritize infrastructure resilience, ensuring that buildings, roads, bridges, and utilities can withstand or recover from seismic events. Early warning systems, currently operational in places like California, can provide residents with seconds to minutes of notice, allowing protective actions that can save lives. Moreover, continuous monitoring and data analysis have led to more accurate probabilistic seismic hazard assessments. These assessments provide regions with estimates of the likelihood of experiencing various levels of seismic intensity over a specified time frame, aiding in risk assessment and planning. Other regions of concern. When contemplating seismic risks within the United States, the spotlight often falls on the prominent and historically active zones, such as the Cascadia subduction zone and the New Madrid seismic zone. While the narrative surrounding these regions is indeed warranted, it's essential to recognize that the tapestry of the country's geology is not limited to these zones alone. Numerous other areas, shaped by eons of geological processes, bear the markers of potential seismic activity. The San Andreas Fault in California is perhaps the most infamous of these regions. Stretching over 800 miles, this fault line has been the protagonist of numerous Hollywood blockbusters, embodying the archetype of earthquake threats. Past events, like the 1906 San Francisco earthquake, stand as testament to its destructive potential. The intricacies of the Pacific and North American plates' interaction along this fault ensure that it remains an area of continual monitoring and study. Moving to the Pacific coast, Alaska is another region that cannot be overlooked. It is one of the most seismically active parts of the United States. The 1964 Alaskan earthquake, with a magnitude of 9.2, remains the most powerful earthquake ever recorded in North American history. Its impact was felt not just in tremors, but also in tsunamis that reached as far as California and Hawaii. Alaska's unique position, with the Pacific Plate diving under the North American Plate, guarantees its continued seismic vibrancy. The Rocky Mountain region, with its rugged terrain and majestic peaks, also holds seismic secrets. Though less active than the coastal regions, historical records and geological studies indicate pockets of seismic activity. The causes here are complex, driven by a combination of tectonic forces and ancient geological structures. Areas such as western Montana and parts of Wyoming, while not frequently in the seismic news, are not immune to significant events. Hawaii, with its paradise-like vistas, is a product of volcanic activity, a different but closely related geological phenomenon to earthquakes. The movement of the Pacific Plate over a hotspot has resulted in a chain of islands, each with its unique geological story. While volcanic eruptions are more common, the region also experiences earthquakes, a reminder of the immense forces at play beneath the surface. Lastly, the Basin and Range Province, stretching from eastern California to central Utah and from southern Idaho into the state of Sonora in Mexico, is characterized by its elongated mountain ranges, separated by down-dropped valleys or basins. This topography is the result of the Earth's crust being pulled apart, leading to both volcanic and seismic activity. It's worth noting that seismic risks are not always about the magnitude of potential earthquakes. The local geology, population density, and built environment play significant roles in determining the actual threat level. An earthquake of a given magnitude might result in minimal damage in a sparsely populated, well-prepared area, but cause significant devastation in a densely populated region with poorly constructed buildings. Earthquake preparedness and risk mitigation. Earthquakes, with their sudden onset and unpredictable nature, stand as some of nature's most formidable challenges. These seismic events, born from the depths of the Earth, have the capacity to reshape landscapes and alter the course of communities in mere moments. Yet, despite their inherent unpredictability, there is one realm where humans hold significant sway: preparedness and risk mitigation. The essence of earthquake preparedness is twofold. Firstly, it pertains to individual and community readiness, ensuring that people are equipped with knowledge and tools to safeguard themselves during seismic events. Secondly, it touches on the broader infrastructural and systemic measures that can be instituted to reduce potential damages. At the individual and community level, education is paramount. Knowledge about safe spots within homes, the importance of securing heavy furniture, and the need to stay away from windows can make a marked difference during an earthquake. Emergency kits, complete with essentials like water, food, first aid supplies, and necessary medications, can be life-saving in the aftermath, especially when critical services are disrupted. Furthermore, communities can benefit from drills and simulations, ensuring that everyone, from children to the elderly, understands evacuation procedures and safe gathering points. However, preparedness doesn't stop at immediate response measures. Building codes play an instrumental role in risk mitigation. Structures in seismic zones need to be designed with earthquakes in mind. This involves considering factors like soil type, potential ground acceleration, and building resonance. Innovations such as base isolators, which allow buildings to move independently of ground motion, and retrofitting older buildings to meet current standards, are vital. Through rigorous codes and their enforcement, the devastation of potential earthquakes can be significantly curtailed. Urban planning, too, holds a key role in risk mitigation. The placement of critical infrastructure, from hospitals to power plants, needs careful consideration. Locating such facilities away from fault lines, ensuring redundancy in critical systems, and designing them to be resilient can make the difference between a community that's paralyzed post-earthquake and one that's able to respond and recover rapidly. Beyond the built environment, land use policies can also contribute to risk reduction. Restricting certain types of development in highly vulnerable areas, such as liquefaction zones or near-active fault lines, can prevent potential future disasters. Similarly, preserving open spaces within urban areas can serve dual purposes, acting as recreational areas in regular times and safe gathering spots during emergencies. At the intersection of technology and preparedness lies the potential of early warning systems. While predicting the exact time and location of an earthquake remains beyond current capabilities, detecting the initial, less destructive seismic waves, P waves, before the more damaging waves, S waves, arrive is possible. Even a few seconds of warning can allow automated systems to halt trains, shut off gas lines, and send alerts to people, enabling them to seek cover. However, for all these strategies to be effective, they need to be underpinned by strong governance and public-private collaboration. Governments play a pivotal role in setting and enforcing standards, investing in research, and raising public awareness. Meanwhile, businesses, especially in sectors like construction, telecommunications, and technology, hold the key to implementing many of these measures. Collaborative efforts, such as public awareness campaigns or joint research ventures, can amplify the impact of individual actions.